Hello, everyone. Welcome to Lecture 11 on Introductory Statistics. Now, in today's lecture, we are going to move on to the next topic, which is independence. So what do we mean by independent events? Now, in general, the conditional probability of A given B is different from the probability of A. Okay, so however, in certain cases, the occurrence of B does not affect the likelihood of the occurrence of A. So in those cases, we say B does not affect the probability of A. Okay, so in other words, whether B occur or not, it doesn't matter to the occurrence of A. Okay, in those cases, we say A and B are independent. So let's consider this definition. That A and B be two events associated with a random experiment. A and B are said to be independent if, all right, the probability of the intersection equals the product of their probabilities. Okay, so this is the definition of independence. All right, if the probability of the intersection equals the product of the corresponding probabilities, then they are independent. Now, otherwise, if they're not independent, we say they are dependent. Okay, so this is the definition of independent events and dependent events. Now here you have to be very careful about two concepts. All right, one is mutually exclusive events. The other is independent events. They are conceptually different. Okay, so be careful. What do we mean by mutually exclusive? Mutually exclusive means their intersection is no event. Okay, so in this case, the probability of the intersection is going to be always 0. Okay, so this is mutually exclusive. Now, because their intersection is no event and the probability of the intersection is 0, so if one event occurs, then the other event can never occur. Okay, so if it is a female, then it can never be a male, right? If it is sunny tomorrow, then it's not going to be rainy tomorrow. Okay, so the occurrence of one event affects the probability of the occurrence of the other, right? So because if one occurs, the probability for the other event is going to be 0. Okay, so be careful on that. This is mutually exclusive events or disjoint events. Now, two events are independent if what? If their this probability, by definition, the probability of intersection is their products. Now, in this case, the probability of the intersection is going to be always greater than 0 as long as what? Their probabilities are greater than 0. So there can never be a mutually exclusive because the intersection is positive, right? The probability of the intersection is positive. So these two are conceptually different concepts. So be careful on that. Let's consider this example. An urn contains 4 balls numbered 1, 2, 3, and 4. One ball is to be drawn at random from the urn. That A, B, C be defined as follows: A, B, and C here. Now we want to determine whether the following pairs are independent. Okay, so now let's consider, let's solve this example solution. Now we know that the sample space is 1, 2, 3, and 4. Since one ball is drawn at random, so they are equally likely. So therefore, the probability of A is simply the number of A, n of A, the number of outcomes in A over m, okay, so which is 2 out of 4, right? So which is 1/2. Now, similarly, we have probability of B equals a probability of C equals 1/2 as well. Okay, so in other words, the probability of A, B, and C, they are all 1/2. Okay. Now let's consider part A. Okay, A. Now, if A and B are independent, how to determine if A and B are independent? Now we know that by definition, we need to check if this equation holds, right? If the probability of intersection equals the product of their probabilities, then they're independent. Otherwise, they're dependent, right? So let's consider if this equation holds for A and B. So now let's firstly check A intersect B. So A and B, we know that intersection is simply this one outcome here. So it's 1 out of 4. That's the intersection. Probability of intersection 1/4. Now, do we have the this equation? So because this one equals what? Well, probably A is 1/2, B is 1/2. So it seems like we do have this equation, right? This equation holds. Now, therefore, hence A and B are independent. Okay, so this is, we verify that A and B are independent by definition, right? So because this equation holds, therefore A and B are independent. Now, how about B? A and C. So we know that probability of A intersect C equals, well, it seems like this is a null event, right? This is a null event, so which equals 0. Now, it seems like, does this equation holds A intersect C? Is this equation a C? Well, it seems that this equation does not hold, right? So this is 0, this is 1/4. So therefore what? By definition, A and C are not independent. All right, be careful, because this equation does not hold. They're not independent, they're dependent, right? And finally, C, A complement. Now, A complement equals 3 and 4, right? So therefore, which equals what? Which equals C, right? A complement is simply C. So what is the probability of A complement intersect B? We see that this is probability 3, right? I think their common here is 3, which is 1/4. And this one equals what? Probability of A complement times probability of B. Because A complement is C, so we have this 1/2. 1/2 times 1/2, that's 1/4, right? So therefore, this equation holds. Now, hence A and C are independent. They are independent, right? Okay, so basically, this is how we can verify if two events are independent, all right? So basically, if to see whether the probability of their intersection is the product of their probabilities. If this equation holds, then they're independent. Otherwise, they're dependent. Okay. Consider this example. Assume probability A is 0.3, probability B is 0.4, A, B are independent. We want to find the following probabilities. Okay, so now A, so probability of the intersection, because they're independent, the probability of the intersection is simply the product of their probabilities. And we can easily see that 0.3, 0.4 equals what? 0.12, right? And similarly, B, probability of A union B, well, this is the probability of the union using what? Addition rule, right? So probability of the first plus probability of the second event minus the probability of their intersection. Be careful, minus the intersection. So what do we have? 0.3 plus 0.4 minus 0.12. So which is 0.58, right? So, and C, okay, so this is A intersect B complement. So this is in A, not in B. So difference rule, it is extract the common part from A, right? So in A, not in B. So using the difference rule, we found this is 0.3 minus 0.12 equals 0.18. And finally, D, probability of A union and B complement. Since it is a union, we use what? Addition rule, right? Plus probability of B complement minus the probability of A intersect B complement. Okay, so probability of A is 0.3. Probability of B complement using the complement rule, we know that it's 1 minus the probability of B, which is 0.4, minus this one we already found in C as 0.18. Okay, so 0.3 plus 0.6, 0.9, 0.72. Okay, this is 0.72. Okay, so that's how we got these ones. Given the independence, the key is we can find the probability of the intersection, and then we use what? Addition rule, difference rule, and another addition rule. Now in this one, in finding probability to be complement, we use the complement rule, right? Okay, very good. Now we are going to move on to section 4, so-called Bayes theorem. All right, Bayes theorem. Now the Bayes theorem is a very important theorem. Okay, so it has really important applications in our real life. Okay, so now we are going to talk about this one. We're in Bayes rule, what we do is we are going to revising a probability value based on some additional information that is later obtained. Okay, so basically you have a probability of an event A, right? So if you have some additional information, right, say some other event occurred, B occurred, right? So what is the probability of A now? Given B has occurred. So this B occurs is some additional information. Well, let's consider the following example. In a certain assembly plant, two machines, B1 and B2, makes 30% and 70% respectively of the products. It is known from past experience that 2% and 3% of the products made by these machines, respectively, are defective. Now, suppose that a finished product is randomly selected. What is the conditional probability that it is produced by B1, given that it is defective? That is to say, we want to find this conditional probability of B1 given it is defective. Now, for this one, we know that without any information, the probability of B1, as we know, is 30% because it makes 30% of the products, right? So probably B1 is 0.3. Now, what we want to find now is, now given it is defective, what is the probability of B1? So now it is probability of B1, all right, given it is defective. Okay, so it's like what? Now we know there is a probability of B1, which is 0.3. We know that, right? So probability of B1 is 0.3. Now, so what if we have some additional information? Now, it is known given that it is defective. So some additional information is later obtained. We know that, and we now know that it is defective. Now, based on this condition, what is the probability that is made by B1? Okay, so it's like what? Revising a probability based on some given information, or updating a probability of an event based on some additional information. Now, how can we find this probability, this revised probability? Okay, so here is my third. Okay, so before we do that, we want to introduce some concepts. Okay, so in this example, I think they make 30%, 70% respectively. So probability B1 is simply 0.3 without any additional information. So this probability of B1 is called the Pereira probability. So the Pereira probability is the probability without any conditional probability. It's simply probability B1. Now, if we are given some additional information that product is defective, then this conditional probability, all right, is called the posterior probability, because now we are given a condition, we are given some additional information, okay? And then what is the probability, right? One is Pereira probability, and then we have posterior probability. Now here is a method how we can solve this kind of problems. Now we just assume that there are 1,000 products. Let's just assume that there are 1,000 products. Okay, so this number can be you can select another number, for instance, 10,000 or 5,000 or some other numbers, but you want to choose a number that is easy for your calculation. Okay, say I'm here using 1,000, but you can use 10,000 or 5,000, like other numbers if you want to. But for this question, I'm going to use 1,000. All right, so 1,000 products. Then we're going to construct the following table. Now this table has here is 1, 2, 3 defective, non-defective total, B1, B2 total, and here I have 1,000. I have 1,000. Okay. Now the second is to complete the table using the given information. Okay, so for the given information from the example, we know that what B1, B2 makes 30% and 70% respectively. Okay, so if we have 1,000 products, all right, in total, now 30% are made by B1. So B1 is going to make what? B1 will be 1,000 times what? 0.3, right? So because 30% made by B1, so that's what? 300. So therefore we have 300 here. Okay, that is what? 300 products are made by B1, and therefore 700 are made by B2, 70%. Okay, so we got these two numbers, 300 for B1, 700 for B2. And then we also give this information that 2% and 3% of the products made by these machines are defective. So 2% of the products made by B1 are defective, or a defective 2% rate, right? Defective rate is 0.02. So if we have 300 so made by B1, now 2% are defective, so is 0.02 times 0.02. So we see that there are 6 on average, right? So 6 of them will be defective because among the 300 made by B1, 2% are defective. So 300 times 0.02, that's 6. So we got 6 here for B1, right? 6 defective ones made by B1. And since this is 6, then because in total that's 300, now we have what? 294 of the products made by B1 are non-defective, are good ones, right? Are good ones. Now, similarly, we can get the information for B2 here, right? So we know that 3% of the products made by B2 are defective. So in total, that's 700 times what? 0.03. So we see that this is 21, right? There's 21 of them. So that's why we have 21 here. Since this is 21, and we see that this is 679 non-negative ones. Okay. Now then if we do the column, the row-wise summation, so 6 plus 21, 27. That's the total number of defective products, right? And similarly, 973 are non-defective ones. So using the information given in the example, we completed this table. All right. So now let's to the next step, using the role for the defective ones to find the probability of what? Of B1, given that it is defective. Now, because here we just focus on the defective one because we know that it is defective, right? It is a defective products. So we're going to zoom in and focus on the defective ones. Now there are in total 27 defective products, among which 6 of them are made by B1, right? So therefore what? This conditional probability is simply 6 out of 27. That's, if you run 3 decimal places, that's 0.222. Okay, so this is how we solve the this problem. Okay, so let's review this problem again. Okay, so you firstly assume there is 1,000 products. You draw this table, and then you complete this table using the given information, right? So especially per probabilities, you find 300 and 700, and then using the defective rate, you find 6, and therefore this one can be found, and then 21, and this one can be found. Then you focus on the first row because the given information is it is defective. So we focus the first row. Now that's 6 over 27. That's the conditional probability. Okay, so the per probability, as we know, probability B1 is 0.3. Now the posterior probability given this additional information is what? Is 0.222, right? So this is up revised probability given some additional information. So this is a per, this is a posterior, right? Okay, so this is the first example we do. Now let's consider another very common problem. Assume cancer has a 1% prevalence rate, meaning 1% of the population has cancer, denoting the event of having cancer by C, and the probability of C is simply 0.01, so 1% for subject randomly selected from the population. Now, the result is included with the following performance characteristics of the test for cancer. Say that we have a test for cancer, screening test for cancer, okay? So we know this one is 0.01, right? 1% prevalence rate of cancer, and false positive rate, all right? False positive rate is 10%. That is to say what? The probability of positive test result given the cancer is not present. Okay, so the cancer is not present. This person is free of cancer. However, what? It got a positive test result, right? So it's a false positive, all right? It's a false positive. So this is a 0.1, 0.10%, 0.10, all right, 10%. And the true positive rate is 80%, which means the probability of positive test result given that the cancer is present. All right, this person has the cancer, and then this screening test will have will give the positive test result has a with probability what 0.8, 80%. This is true positive, right? It has cancer and it got a positive result, so that's true positive rate. Now, what do we want to find? We want to find the probability of cancer given a positive test result. That is, to find the probability that a subject actually has cancer given that he or she has a positive test result. Okay, so as we know, the prevalence rate of probability C is 0.01. This is per probability. We know that this is 0.01. And what we want to find is a probability of C given what? A positive test result, right? So positive test result is some additional information. And then this conditional probability is what? Is the posterior probability, okay? Now, let's see how can we find this probability. So again, we assume there's 1,000 individuals in the population and construct this table, right? And then we're going to complete the table using the given information. Now, the Pereira probability is what? Pereira probability per C is 0.01, right? 0.01. So if this is 1,000, how many of them will have cancer? So that's going to be 1,000 times what? 0.01, which equals 10. So we're going to have the cancer. Well, now it becomes the row sum, right? Here is going to be 10, right? 10 of them will have cancer. Now, of course, 990 will not have cancer, right? 990 will not have cancer. Now, we say that there's a false positive rate of 10%. False positive. False positive means what? Means cancer is not present, all right? Then there is a positive test result is 10%. So that is to say, among the individuals without a cancer, that's 990 of them, 10% will have positive test result. So 990 times 0.1, that's what? 99, right? So 99 of them will show cancer. That's a positive test result. Then 99 minus 990 minus this 99, that's what? 889, right? 889. Another information is, well, this is true, false positive rate is, oh, wait. Sorry. Sorry about this. Okay, did make some error here. Okay, so true positive rate is false. Well, yes, it's right. That's right. Okay, so this is 99. It's 889. Okay, 889. Oh, yes, that's right. Now, then the true positive rate is 80%. Now, given the cancer is present, so the positive rate is 80%. So among these 10, 80%. So that is to say 8 of them will show there is a cancer. 2 of them shows there's no cancer, right? So among this 1,000, how many of them will show cancer? Test result. So 99 plus 8, that's 107. Now, how many of them will show that there is is that right? Did I make some error in the calculation? Oh, 891. So sorry. So this is 891, right? So sorry about that. This is going to be 900. 893. All right, 893, right? So that's right. Okay, so we have completed this table based on the information. Okay, so now we are going to use the rule for cancer to find, actually this should be the column, right? The column for positive result. Okay, so it's a column. So what is the, we're going to, because the given the additional information is a positive test result. So we're going to focus on the first column, right? The first column. So out of this 107 with the positive test result, actually there are only 8 of them with cancer, right? So therefore, the probability of cancer given a positive test result equals what? Equals, in total we have 107. There are 8 of them, right? 8 out of 107. Okay, so in this one we have the posterior, the Pereira probability is 0.01, and then if it has a positive test result, this conditional probability result became what? 8/107. All right, it's less than 8%, right? So now this is the prior, this is the posterior. Okay, so here is one interesting observation is what? Even though you have a positive test result, the chance of cancer is still pretty low. It's less than 8%, right? So 8/107. So that's still pretty low. You don't have to worry too much, even you got a positive test result. Now, the reason why we have such a, even you have a positive result, this posterior probability is still very low, is because what? It's because majority of what the people who are tested positive, this 107, is what? Are false positive, right? So 99 of them show positive result, but they do not have cancer, right? So majority of them are false positive. So a prior probability is initial probability value before any information is obtained. Posterior using some additional information. Okay. All right. I think that's all about this this chapter on probability. Now we're going to move on to the next chapter about random variables. Okay, about random variables. Now, firstly, let's consider what is a random variable. Now, a random variable is a variable denoted by a capital letter, either capital X, Y, or Z, so on. So, which has a single numerical value for each outcome of a random experiment. Okay, so if you remember, a random experiment is a process or procedure with more than one possible outcomes, right? So it assigns a numerical value to each outcome in the sample space. Okay, so that is a random variable, right? So it is a variable which has a single numerical value. All right, so it has a numerical value for each outcome of a random experiment. It assigns a numerical value to each outcome in the sample space. Let's consider this example. All right, consider the flipping of a coin. X be a variable that takes a value of 0 if a tail is obtained, takes a value of 1 if a head is obtained. Okay, so here X has a single numerical value, right, determined by chance for each outcome of this procedure. So it equals 0 numerical value if a tail is obtained. And equals 1 a numerical value if a head is obtained. So it's like what? It assigns 0, this numerical value, to the outcome tail, and assigns 1, the numerical value 1, to the outcome head. Okay, so by definition, what? My X is a random variable. So X equals 0, X can be equals 1, right? So now consider this example. We want to find all the possible values of the random variable X. Okay, consider tossing a fair coin twice successively. And X be the sum of the two tosses. Okay, so what are the possible values of X? As we know, a fair die is 1 through 6, right? So the minimum possible value is when both tosses are 1s, right? So 1 for the first, 1 for the second. In this case, the summation will be what? 2, right? So 2 is the smallest possible value. And the summation can also be 3, right? Can also be 4. The maximum will be what? Maximum will be when both dice results a 6, right? So 6 plus 6, that's 12. So these are the possible values of X. Consider B. X be the number of interviews needed in order to fill an opening for a country. Okay, so one opening here, so you need at least 1 interview, right? So I believe this is 1, right? Is that possible for X equal to 2? Do you need 2 interviews for this 1 opening? I think this is okay, right? So because maybe the first interview failed, and then you need a second interview and it is successful. So in this case, X can be 2, right? So how about 3? So 3 is also possible, right? So first 2 interviews are all failed, but the third one succeeded, right? So 3 is also possible. And if you repeat this process, then it can be what? Any values, any positive integers, 1, 2, 3, 4, 5, into infinity. C, the X be the time needed for Jim to complete a 15 minutes exam. Assume that every student needs at least 20 minutes to complete the exam. Okay, so now for this one, it can be the time, right? The time to finish this exam. So at least 20, so 20 minutes at the minimum, right? Including the 20. It can be what? Time, because time, it can be literally any value in that interval, right? So the maximum is 50 minutes, right? So basically that X can be any value from this interval, right? From 20 minutes to 50 minutes. So it can be also decimal points, right? 20.1, 20.001, right? And so on. So it can be decimal points as well. So in other words, we can use this interval to represent all the positive, all the possible values of X. D, and let X be the lifetime of the electronic component used in a space station. So for this one, the lifetime can be what? Any positive constants. So 0 to infinity, right? 0 to infinity. The lifetime, right? So it's 0 to infinity. Now, for these 4 cases, now we see that for the part A, there are a finite number of possible values, right? So there are what? I think there are 11 possible values, right? 11 possible values. And for the second, how many are there? 1, 2, 3 till infinity, right? So I think there are infinite many possible outcomes. Now, how about C? How many possible values are there in this interval? In this interval, because the decimal points are also inside the interval, so if you count the decimal points, then what? It is also infinite, right? It's also infinite. And now, if this is infinite and this is also infinite, are they the same? Do they have the same amount of values? They're both infinite. Okay, so no, the answer is no, they are different. Okay, for B here, it is called countably infinite. Okay, so these values can be put in a sequence, all right, a list. So 1, 2, 3, 4, and so on, right? So it is countably infinite. However, for this interval here, it is not countable, all right? It is infinite, but not countable. Now, why? What do you mean by not countable here? Okay, so it is not countable because, can you find out, for instance, now in the in B, right? After 1 you have 2, after 2 you have 3, after 3 you have 4, and so on, right? You can list them in a sequence. Now, can you tell me what is the next value right after 20? Is that 21? It's not 21, right? So I have 20.1. 20.1 is closer to 20, right, than 21. So the next value is 20.1. No, I also have another value which is closer to 20, right? So say 20.01, right? It's closer to 20, but then 20.1. Then is that 20.01? The very next value after 20? You also have 20.001, right? And you see that there is really no next value right after 20. In other words, these values cannot be listed in a sequence. It's not countable. Right? It's not countable. So the fact is there are 4 more elements in this interval than the sequence in B. All right, so this is infinite but not countable. Now, however, this interval, even though it is infinite and not countable, it is what? Bounded. It is bounded. All right. You have a lower limit 20, upper limit 50. So it is bounded. Okay. Now for part D here, now this one is what? From 0 to infinity. Now, of course, this interval is larger than the interval in C, right? It's larger than C. So of course, it's going to be also infinite, but not countable. Yes. Because this is larger than that, right? And also what this interval is going to be what? Is unbounded. It's not bounded, unbounded, right? Because it goes to infinity, right? There's no upper limit. Okay, so you can see that from this example, there are different types of random variables, right? So they're all random variable. However, there are in A, there are finite number. In B, there are countably many. In C, it's infinite but not countable. However, it is bounded. In D, it is infinite, not boundable, and unbounded, right? So we have different kinds of random variables. Now, in this chapter, we are going to focus on the first 2 cases. Either they have finite number of possible values or countably infinite. So that is a discrete random variable. So what is a discrete random variable? It's a random variable that has either finite or a countably infinite number of possible values. Well, a continuous random variable is a random variable that can take any value from an interval, right? Like what we have in these 2 cases. Now, let's consider this example. Determine whether the following random variables are discrete or continuous. The number of girls in a randomly selected 4-child family. So is this discrete or continuous? This is what? Discrete. So what are the possible values? How many are there? How many possible values for this number of girls? There are what? Be careful, there are 5 such possible values, right? And maybe what? Maybe 0, right? This number of girls can be 0, then all the 4 child are boys. 0, 1, 2, 3, 4. So there are a finite number of possible values. Okay, so therefore it is discrete. And B, the number of accident-free days in a 30-day period in a factory. Okay, so the accident-free, so this is number of days, so it is also discrete. What are the possible values? It may be 0, right? Every day has an accident. And so in this case, the number of accident-free days will be 0. Can be 1, can be 2, can be 30. So there are 31 possible values. So therefore it's again finite, all right? The duration call to 911. So this is what? It's a time, right? So it can be any value from an interval, so it's a continuous. Air pressure of a carrying truck is also what? Continuous. Because it can be any value from an interval. Okay. All right. Now, for discrete random variables, we have a probability distribution. Okay, so it is a description that gives a list of possible values of X and the corresponding probability values. Okay, so for each possible value of x, it is often expressed in the form of a table, formula, or graph. Now, let's consider this example. Tossing two fair coins randomly, the sample space is this. Let x be the number of heads among these two tosses, a number of heads, okay? So what are the possible values of x? So number of heads, x can be what? X can be maybe 0. There's no heads among these two, right? So in this case, it's a tail, right? So the number of heads will be 0. And also it can be 1 and what? And 2, right? So 0, 1, 2. So maybe 2 heads, right? 0, 1, 2. What is the probability of 0 is the probability, the number of heads is 0. Okay, so P of 0 equals probability for x equals 0. X equal to 0 means there's no heads, so which is a tail. So what is the probability getting a tail? So it's 1 out of 4, right? Similarly, probability of 1 equals x equals 1. Now, x equals 1 means the number of heads is 1. So 1 means what? Maybe head, tail, or tail, head, right? So that's a 2 out of 4, which is 1/2. Finally, P of 2 equals probability x equals 2 equals what? The number of heads is 2, so that's what? Simply 1, 1, right? So 1 out of 4. 1 out of 4. Okay, so we have the list of possible values 0, 1, 2, and also here gives the corresponding probabilities. Okay, P of 0, P of 1, and P of 2. Now, it is often expressed in the form of a table. So we can let's put this one in a table. So we can have such a table. Here is x, 0, 1, 2. And the second row, P of x, here is 1 over 4. Here's 1/2. Here's 1 over 4, right? So this table, okay, give us what? The list of possible values 0, 1, 2, and also their corresponding probabilities, right? So this table gives us the probability distribution of this random variable x. Now the probability value P of x have the following properties. Now, firstly, the possible value of x must be what? Numerical values. It must be numerical values. Two, the probability values must be between 0 and 1. So as you can see, 1 over 4, 1 over 2, 1 over 4, they're all between 0 and 1. And finally, the sum of the probability must be 1. In some cases, the sum can be might not be exactly 1, but very close to 1, such as 0.99, 1.001, due to rounding error, right? Due to rounding error. So, for instance, this one, 1 over 4 plus 1/2 plus 1 over 4, this is exactly 1. Right? This is exactly 1. The total probability must be 1. Now consider this example. All right, check if the following descriptions represents a valid probability distribution. A, consider a survey on self-driving vehicles. Let X be the number of adults who feel comfortable in a self-driving vehicle among a random sample of 4 adults. Okay, so the possible value of X is 0, 1, 2, 3, 4. P of X are given here. So I believe these are all numerical values, right? Where numerical values, the possible values of X are numerical, right? 2, I think all these are probability values. Probability values are what? Between 0 and 1. Okay, so they're all between 0 and 1, as we can see, right? And thirdly, the summation. So if you take the summation 0.350 plus 0.121 plus plus 0.148, if you add them up, you will get what? 0.999. Okay, so using the calculator, you can find that this summation is 0.999, which is Very, very close to 1, right? So because this might be due to a rounding error. So as we said, these are 3 conditions all holds. So therefore what? This yes, all right, yes, it is a valid probability distribution. B, now let X be the number of classes that the randomly selected students has missed. Assume the maximum number of absences allowed is 3. So X can be 0, 1, 2, 3. So P of X are given here. All right, so is this a valid probability distribution? So 1, there are numerical values, right? Numerical values, 0, 1, 2, 3, right? 2, they're all between 0 and 1. I believe it's between 0 and 1, right? So between 0 and 1. The 3, so it's a summation. 2 plus 0.83 plus 0.230. This equals what? I believe this is 0.686. Okay, so now this is not even close to 1, right? So this does not equal to 1. Okay, so actually it's pretty far away from 1. So therefore what? This is no, right? No, it is not a valid probability distribution. Now, how about C? Hiring managers were asked to identify the biggest mistakes that job applicants made during an interview. The table below is based on their responses from a survey. Is this a probability distribution? How do you think? Yes or no? Now, this one is actually no, right? No, why? Why? Okay, so you see these are what? Not numerical values. All right, so the first is numerical value. This one does not hold, right? So they are not numerical values, they are categorical values, right? So therefore what? This is not a valid probability, okay? So even though all these are between 0 and 1, their summation is 1, but the possible values X is not numerical, so therefore it's not a valid probability distribution. D, let X be the number of car accidents occurred in a randomly selected day in a small town. Assuming the possible values of X are 0, 1, 2, 3, the possibility values are given in the following function. Okay, so the possible values are 0, 1, 2, 3, they are numerical. So numerical, right? Numerical values of X. 2. They're all between 0 and 1, right? So 3 plus 1, they're all between 0 and 1. Now, let's see, what is P of 0? Equals F of 0 equals 0 plus 1 over 10. That's 1 over 10, right? So similarly, P of 1 equals 1 plus 1 over 10. That's a 2 over 10. P of 2 equals 2 plus 1 over 10. So 3 over 10. And finally, P of 3 equals 3 plus 1 over 10. That's a 4 over 10. Okay, so we're going to have all these values are between 0 and 1, right? So 3, the summation is what? So 1 over 10 plus 2 over 10 plus 3 over 10 plus 4 over 10 equals 1. Okay, so the summation is 1. So therefore what? Yes, right? Yes. This is a valid probability distribution. Okay. Now let's consider another example here. Roll a fair four-sided die twice, but X be the lot. Well, let's say that this is not larger, but maximum. X be the maximum value of the 2 rows, and the sample space of this random experiment is given here. We assume that each of these 16 outcomes has a probability of 1 over 16. Okay, now let's just rewrite the sample space so that it's clear now. All right, it's 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, and 3, 1, 3, 2, 3, 3, 3, 4. Okay, 4, 1, 4, 2, 4, 3, finally 4, 4. Okay, so this is our sample space. So because X is the maximum value among these two tosses, so each of them is 1 through 4. So I would say the possible values of X are what? The possible values of X are, it can be 0, cannot be 0, right? So because the maximum of the two can be 1, right? 1 if what? If you got a 1, 1, then the maximum of the two is 1, right? It can also be 2, right? Can 2 if what? If you got 1, 2, the maximum is 2, 2, 2, the maximum is 2, 2, 1, the maximum is also 2, right? So it's the possible value of X can also be 2. Similarly, it can also be 3. So, okay, so 3, and finally what? And 4. Okay, so, and 4. Okay. So find the corresponding probability values. Okay, so P of 0, P of 1, all right. Probability for X equals 1. Now it's going to be 1, 1, so 1 out of what? 16, right? Similarly, P of 2 equals P of X equals 2. X equal to 2, there are 3 possible values, so it's 3 out of 16. Okay, P of 3 equals probability for X equals 3. This one equals 1, 2, 3, 4, 5, 6, 4, 5. So 5 over 16. And finally, P of 4 equals X equals 4 equals what? 3, 4, 5, 6, 7. So it's 7 out of 16, right? 7 out of 16. So these are the corresponding probability. Then we want to construct the probability distribution. So we have X can be what? 1, 2, 3, 4. And P of X, here is 1 over 16, 3 over 16, 5 over 16, and 7 over 16. Right? 7 over 16. And we want to find the probability for X greater or equal than 3. So greater or equal to 3, that can be what? X equal to 3 plus probability for X equals 4, right? So this one equals 5 over 16 plus 7 over 16. So as 12 over 16, so 3 out of 4, okay? X takes odd numbers. So probability that X is odd is what? X equals 1, or probability for X equals 3. So 1 over 16 plus 5 over 16, 6 over 16 is 3 over 8. Right? Okay. All right. So I think that's all we're going to cover in this lecture, and I will see you in the next one. Thank you.